59 minutes, just under an hour. That's how long it took a scramjet prototype to scream from a remote test facility in Nevada to the tumultuous waters of the South China Sea last year. All without a single human pilot aboard, no cumbersome tankers for refueling, and certainly no warning for anyone caught unaware. Imagine that. 1 minute later, almost before the sonic boom had fully dissipated across the waves, that same craft's AI wingman unleashed a swarm of 30 microdrones. These tiny, buzzing eyes and ears, working in perfect silent concert, mapped an entire island chain with astonishing precision before the first cup of coffee even hit the Pentagon's war room table. The era of the lone fighter ace, that iconic image of daring and individual skill, is over. It's not just fading, it's been decisively eclipsed. We've entered, almost without realizing it, the age of thinking, swarming, hypersonic machines. If you blinked, if you weren't paying close attention, you didn't just miss a moment. You missed the starting gun of a whole new chapter in warfare. The future of military aviation isn't coming. It's already here, taking off at Mach 5 and beyond. The new brains, AI and drone swarms. Take a look at Ukraine today and you're witnessing something truly unprecedented. The first large-scale, real-world audition for robot air warfare. It's a stark, brutal proving ground. There, a $400 quadcopter armed with nothing more than a hand grenade can stalk and disable a $5 million tank. Think about that cost disparity for a moment. Now multiply that by 1,000 or 10,000, and you start to grasp what military planners are now calling replicator economics. It's a game changer. Cheap, fast, and practically disposable. This isn't about building one perfect, expensive machine. It's about fielding an overwhelming number of good enough machines that can achieve mission success through sheer, relentless volume. The psychological impact of facing an endless, relentless swarm of inexpensive, intelligent drones is arguably as devastating as their physical destruction. The next, inevitable step in this evolution is full autonomy. Right now, in many current operations, a human still squeezes the trigger, often through a satellite link. But this reliance on a remote operator introduces critical vulnerabilities. Latency, the fractional delay in signal transmission, can be the difference between success and failure, and jamming, the deliberate disruption of communication, can render even the most advanced drone utterly useless. These factors make the human-in-the-loop system inherently fragile in a contested electromagnetic environment. So engineers are pushing the decision-making loop inside the drone itself. They're embedding sophisticated AI that can process information, make choices, and execute actions with machine speed efficiency. Modern graphics chips, initially designed for the hyper-realistic demands of video games, are proving to be perfect for this task. These powerful processors can run complex neural networks that can, for instance, spot a T-72 tank turret hidden in dense foliage in just 0.3 seconds. More than just identification, the AI then decides whether to attack, calculates the optimal approach, and maneuvers the drone to hit the weakest armor angle. There's no joystick for a human to manipulate, no lag from a remote connection, and absolutely no mercy in its cold, calculated execution. This isn't just automation. It's autonomous lethality, operating at a speed no human could ever hope to match. The Pentagon's Skyborg program, a vanguard effort in autonomous combat, showcased this capability spectacularly last March. An AI pilot, flying an XQ-58 Valkyrie unmanned combat aerial vehicle, was put through its paces in a simulated combat scenario. During this critical test, the software wasn't just following a pre-programmed flight path. It had to dynamically choose between two active surface-to-air missile sites, intelligently route around a civilian airliner that appeared unexpectedly in its flight path, and still precisely deliver a glide bomb on its designated target. It succeeded, completing this complex sequence of decisions and actions faster than the human chase pilot. Flying alongside in an F-16, could even finish reading his emergency checklist. This wasn't just a triumph of code. It was a testament to the AI's ability to process, adapt, and execute under pressure, far exceeding human cognitive limits. What's even more astonishing, that same core algorithm, that powerful digital brain, is now being shrunk onto a circuit board that weighs a mere 780 grams, light enough to stuff inside a hobby-grade racing drone, the kind you can buy online today. Think about the implications. Tomorrow's Air Force might not just be a fleet of billion-dollar jets, but potentially a crate of sophisticated electronics you can purchase from an e-commerce site. It democratizes advanced air power in ways we're only just beginning to comprehend. Swarming, without a doubt, is the ultimate force multiplier. Instead of investing in one exquisitely expensive $80 million fifth-generation fighter, a commander could, for the same price, acquire 2,500 intelligent drones. The strategic shift here is profound. Imagine releasing these drones 50 kilometers from an enemy radar station. They don't fly in a rigid formation. They negotiate in midair. A distributed self-organizing network. Who goes high? Who goes low? Which units carry electronic jammers to blind the enemy? And which carry warheads for the decisive strike? If 20 of these drones are shot down by enemy defenses, the remaining 2,480 instantly replan their attack, adapting their tactics on the fly. There's no self-pity, no medals for bravery, no letters to send to grieving families. The math is brutal, cold, and undeniable. Even the most advanced multi-million-dollar air defense missile often costs significantly more than the drone it manages to kill. This means defense budgets bleed to death, one expensive interception at a time against an adversary that is practically infinitely replenishable. This isn't just a new tactic. It's a new economic model of warfare. The new speed. Hypersonics and the one-hour weapon speed has always been a weapon in warfare. A critical advantage that dictates who strikes first, who escapes, and who survives. But hypersonics? That's not just speed. It's a whole new dimension, effectively turning travel into a time machine. We're talking about anything above Mach 5, 5 times the speed of sound. At these velocities, an aircraft doesn't merely fly. It practically bends the laws of physics as we understand them. The sheer kinetic energy involved is staggering. Air molecules, normally an invisible medium, slam into the craft's nose at thousands of degrees Celsius, hot enough to melt copper instantly. This isn't just an engineering challenge. It's a materials science nightmare. That's why the craft's skin isn't made of conventional metals. It's grown from exotic carbon composites, similar to those that once protected the bellies of space shuttles during their fiery re-entry. At such incredible speeds, a vehicle launched from New York could circle the entire globe and return before a conventional bomber has even finished its first mid-air refueling over the Atlantic. This isn't just faster travel. It's a complete redefinition of global reach and response. But here's the real breakthrough, the secret sauce that elevates hypersonics beyond mere velocity. It's not just raw speed. It's controllability. Old ballistic re-entry vehicles, once launched, were largely slaves to Isaac Newton's laws of gravity and motion. They followed predictable parabolic trajectories, making them, in theory, interceptable. New hypersonic glide vehicles, however, are a different beast entirely. They don't just fall. They actively ride the upper atmosphere, soaring like a surfer on a 30-kilometer high wave. They can bank at extreme 40-degree angles, executing evasive maneuvers to dodge interceptors or change targets mid-flight. China demonstrated this terrifying capability in 2021, when one of its hypersonic craft performed an unprecedented feat. It dropped a separate, smaller missile mid-flight, a trick no one thought possible at Mach 10. The message sent was chillingly clear. Even if you manage to track the primary weapon, the final lethal sprint can originate from somewhere entirely unexpected, leaving defenses scrambling and often futile. The vision isn't just for massive one-off missiles. Hermes, an ambitious startup backed by the U.S. Air Force, is working to scale this concept down to reusable jets. Their quarter-horse demonstrator is designed to take off like a regular airplane, accelerate to an astonishing Mach 5, deliver its payload, turn around, and land, ready to fly again the very same afternoon. If they pull this off, the implications are monumental. The vast expanse of the Pacific Ocean, which currently takes hours for military aircraft to traverse, would effectively shrink to the size of a pond. A single base in Guam could put Tokyo, Taipei, Manila, and even Pyongyang under the same 30-minute bubble of deterrence. This capability fundamentally alters strategic calculus, dramatically reducing response times and projecting power with unprecedented agility. Critics, naturally, are quick to point to the astronomical costs. The unit flyaway cost for an AGM-183A air-launched hypersonic missile hovers around $18 million, which is roughly one-third the price of a cutting-edge F-35 fighter jet. That sounds expensive, right? But compare that price tag to the immense cost of keeping an entire carrier battle group on station for 6 months, factoring in fuel, personnel, maintenance, and support ships, and suddenly the ledger flips dramatically. Speed in this new paradigm is proving to be far cheaper than steel, especially when you don't have to worry about keeping fragile, vulnerable humans inside the weapon. This isn't just about faster delivery. It's about a more efficient, less resource-intensive way to project decisive force. The new Apex Predator, 6th-generation fighters. Every 30 years or so, the counter on fighter generations ticks over, marking a profound leap in capability. We are now standing squarely on the doorstep of the 6th. The United States Air Force's NGAD, Next Generation Air Dominance, the Navy's FAXX, Europe's FCAS, Future Combat Air System, and the UK, Japan, Italy GCAP, Global Combat Air Program, are all distinct programs, but they are chasing the same 4 foundational pillars. These aren't minor upgrades. They represent a fundamental reimagining of air combat. First, stealth beyond today's imagination. We're talking about levels of low observability that make current stealth aircraft look like Christmas trees on radar. This isn't just about reducing radar cross-section. It's about making the aircraft virtually undetectable across multiple spectrums, from radar to infrared to radio frequency emissions. Second, adaptive engines that are revolutionary in their design. These power plants can sip fuel efficiently during long-range cruise missions, then instantly guzzle it to deliver maximum thrust in a dogfight. Third, sensors that fuse data from space to sea. This means an unprecedented level of situational awareness, integrating information from satellites, ground sensors, naval assets, and other aircraft into a single, cohesive picture for the pilot. And fourth, and perhaps most crucially, a mothership role for drones. This isn't just about flying alongside. It's about command and control of a loyal, intelligent, and expendable fleet. Picture this: a cockpit where the pilot's helmet isn't just showing the sky ahead, but also a seamless real-time feed from 3 loyal wingmen flying 20 miles away, each carrying extra missiles, advanced sensors, or electronic warfare payloads. The human pilot, the strategic brain of the operation, decides the overarching strategy, the mission objectives. The AI, the tactical genius, handles the micro-tactics, the split-second decisions that would overwhelm a human. If an enemy radar suddenly lights up, one drone can instantly peel off to jam the signal, protecting the manned fighter. If a missile is launched, another drone can sacrifice itself, drawing the incoming threat away from the crewed aircraft, keeping the human pilot hidden and safe. The result? A single NGAD aircraft doesn't just represent one fighter. It brings the coordinated firepower and sensor capabilities of 4 legacy jets, but for roughly the cost of 2, and crucially, without risking 4 human crews. It's an exponential leap in combat efficiency and risk mitigation. The engines themselves are a revolution. A variable cycle power plant isn't just more powerful, it's transformative. It can act like a high-bypass turbofan for long-range, fuel-efficient transit, then instantly morph into a low-bypass turbojet for raw, unadulterated thrust during combat. This adaptability promises significant gains. Expect 25% better fuel burn and a 30% greater combat radius than an F-35, even while carrying heavier, more advanced payloads, including directed energy weapons. Yes, lasers. We're not talking about science fiction anymore. Solid-state laser modules are rapidly advancing, on track to hit 300 kilowatts of power by 2027. That's enough raw energy to burn a hole clean through a cruise missile at 5 kilometers in just 10 seconds. Imagine, no bullets, no ammunition limits, no gun jams, just a focused beam of pure electricity straight from the engine's power core. This fundamentally changes aerial combat, offering precision, speed, and virtually unlimited ammunition as long as the aircraft has power. Stealth, too, is moving beyond just angular designs and radar-absorbent paint. It's going skin deep, becoming an inherent property of the aircraft itself. New metamaterials are being developed that can actively bend radar waves around leading edges and surfaces, effectively making them disappear rather than just absorbing them and reflecting a tiny fraction back. And if that wasn't enough, imagine adding a coating that changes color with voltage, allowing an airplane to instantly fade against any sky, from Arctic white to desert tan, without a single drop of paint. Rivet counters, those aviation purists who obsess over every detail, will absolutely hate it. But enemy radar operators? They'll fear it because they simply won't see it coming. Convergence. When swarms, speed and stealth collide. The real leap, the truly transformative aspect of this future, isn't any single gadget or groundbreaking technology in isolation. It's the invisible yet incredibly powerful glue that binds them all together. The Air Force calls it Joint All-Domain Command and Control, or JADC2. Classic Pentagon jargon, yes, but it describes something profound. Think of it as a hyper-advanced nervous system for the entire battlefield. A vast resilient mesh network that links satellites, airborne tankers, stealth fighters, drone swarms, naval ships, and even ground troops. Every sensor, no matter how small or distant, becomes a node in this network. Every shooter, from a hypersonic missile to a soldier's rifle, becomes a service available on demand. Data doesn't just flow. It hops across aircraft, leaps across orbital platforms, reroutes seamlessly under cyber attack, and still arrives at its destination in milliseconds. The battlefield isn't a collection of disparate units. It becomes a single sentient organism, and its speed is measured not in kilometers per hour, but in the instantaneous speed of thought and data processing. Imagine this future raid, a scenario that might sound like science fiction but is rapidly approaching reality. A B-21 Raider, a stealth bomber so advanced it's barely a whisper on enemy radar, releases a hypersonic glide vehicle from outside enemy airspace, hundreds of kilometers away. The weapon screams in at Mach 7, a silent, blazing arrow across the sky. But instead of a conventional warhead, it carries a canister, a miniature Trojan horse filled with micro-drones. At precisely 30,000 meters, high above the atmosphere, the canister bursts open, and the drones spread like seeds on the wind, each one a tiny, intelligent sensor. As they descend, each micro-drone snaps high-resolution photos, listens to radio chatter, and beams its trove of intelligence back to an NGAD fighter loitering 600 kilometers away, still safely beyond any immediate threat. The fighter's onboard AI, processing terabytes of data in real time, identifies mobile missile launchers hidden under highway bridges, launchers that would be invisible to conventional reconnaissance. It doesn't just identify them, it predicts their next move. The AI then assigns targets to nearby drone swarms, which have been patiently waiting ready for their cue. These swarms, acting as one, dive and kamikaze into the launcher's radar cabins, blinding them, rendering them useless. Total elapsed time from the hypersonic release to the eerie silence that follows the neutralization of the threat? A mere 12 minutes. No humans crossed the border. No pilot breathed heavy G-forces or risked their life. Yet the enemy's anti-access bubble, designed to keep forces out, is punctured, and at a cost of only a few $100,000 in expendable hardware. This isn't just warfare. It's surgical, autonomous, and devastatingly efficient. This convergence fundamentally alters the nature of both attack and defense. It shifts the advantage dramatically towards the side that can integrate its systems most effectively, process information fastest, and unleash coordinated multi-domain attacks with machine precision. Defending against such a distributed, intelligent, and hyperfast threat becomes a nightmare, as traditional defenses designed for single, identifiable targets are overwhelmed by a torrent of coordinated, diverse attacks coming from multiple vectors simultaneously. The human factor, pilots, programmers, and ethics. While technology surges forward exponentially, biology regrettably remains flat. A fighter pilot still blacks out at 9 Gs. A coder still needs coffee and sleep. The future cockpit, then, is less about the visceral, tactile feel of leather straps and more about the elegant, intuitive simplicity of language. Pilots won't be wrestling with physical controls as much as they'll be speaking to their machines, much like we talk to smart speakers or virtual assistants today. Imagine. Ghost 1, screen left, launch decoy, jam band 10. Rejoin in 30 seconds. The AI, the loyal wingman, answers in plain English, not cryptic acronyms or complex button sequences, confirming its understanding and execution. This means training shifts dramatically. Less time on stick and rudder hours, more on algorithmic trust exercises. Can you truly hand your life and the success of a mission to code written by a 25-year-old civilian contractor? That's a trust exercise unlike any before. This brings us to the thorny, inescapable issue of ethics. particularly concerning lethal autonomy. Ethics boards worldwide are already wrestling with the profound implications. The Pentagon's current policy, a carefully constructed barrier, still requires a human in the loop for any decision to take a human life. But this loop is stretching, becoming thinner and more precarious by the day. Consider a hypothetical yet increasingly plausible scenario. A hypersonic drone detects an imminent nuclear missile launch, a threat requiring an immediate, decisive counterstrike. If that drone has only 120 seconds to prevent a global catastrophe, waiting for a satellite uplink to a human operator, who then has to assess the situation and give approval, could mean catastrophic failure. Lawyers and philosophers argue endlessly about appropriate levels of human judgment and the moral accountability of algorithms. Meanwhile, engineers focused on mission success and efficiency are quietly shortening that chain, automating more and more decision points. The slope is undeniably slippery, and frankly, nobody has posted any speed limit signs. The implications for accountability for the very definition of warfare are staggering. Who is responsible when an autonomous system makes a lethal decision? This isn't just a philosophical debate. It's a pressing legal and moral challenge that demands answers before the technology outpaces our ability to govern it. Public perception lags even further behind the technological curve. Hollywood still churns out blockbusters depicting dystopian robots run amok, while ironically, your local hobby shop sells sophisticated drones that can follow you downhill on a snowboard with impressive autonomy. Bridging this enormous gap between public fear and technological reality is absolutely vital. Why? Because democracies simply will not fund what they fear or what they fundamentally misunderstand. The most advanced air force on Earth, operating at the bleeding edge of AI and robotics, is still ultimately voted on and paid for by people who, through no fault of their own, might think stealth technology is something out of a ninja movie. Educating the public, building trust, and fostering a nuanced understanding of these complex systems is as critical as the engineering itself. If these advancements are ever to reach their full potential and be responsibly deployed, the democratization of advanced military capabilities, as seen in conflicts like Ukraine, also means that asymmetric warfare is becoming more sophisticated, forcing a re-evaluation of traditional power balances and the ethical frameworks that govern them. The global chessboard. Who leads? Who chases? In the high-stakes game of military innovation, money is undeniably the true mother of invention. The United States, a perennial leader in defense spending, is projected to funnel roughly $56 billion into next-generation aviation research and development over the next 5 years alone. This colossal investment is aimed at maintaining its qualitative edge. China, the rapidly ascending challenger, operates with a budget that is notoriously opaque. However, open-source satellite photos, a modern form of intelligence gathering, clearly show two separate NGAD-style prototypes, their own sixth-generation fighter equivalents, taxiing at the Chengdu aircraft plant. Beijing isn't just walking, it's sprinting to catch up, and in some areas it might even be pulling ahead. Washington, by comparison, sometimes appears to be jogging. Burdened by bureaucratic processes and legacy systems, Europe, meanwhile, finds itself somewhere in between, wisely recognizing that no single nation on the continent can realistically foot the bill for a full-fledged sixth-generation fighter program alone. This realization has spurred unprecedented collaboration. The UK's Tempest program, for example, transformed overnight into the Global Combat Air Program, GCAP, when Japan brought its formidable engine technology and manufacturing prowess to the table, and Italy contributed significant financial backing and industrial expertise. This pooling of resources is crucial for smaller, yet technologically advanced nations to remain competitive. Russia, cash-strapped and facing significant economic headwinds, is banking on a different strategy: clever software. Their gamble is to develop advanced AI and networking capabilities that can turn their existing, albeit aging, legacy fighters into effective drone controllers, hoping that the quantity and sophistication of their code can effectively beat the quality and sheer expense of Western hardware. It's a high-stakes bet on digital supremacy over material advantage. Export rules, too, are undergoing a seismic shift. Yesterday's F-22 Raptor, a pinnacle of fifth-generation stealth technology, was permanently banned from foreign sales, a tightly guarded technological secret. Tomorrow's Loyal Wingman drone, however, might be cleared for export to key allies next week. The calculus behind this change is simple yet profound. If you can buy the accessory bots, the intelligent, expendable drone wingman, maybe you don't necessarily need to acquire the flagship multi-billion-dollar crewed fighter. This new terrain favors middle powers like Australia or Sweden, nations that can't afford to develop their own cutting-edge fighters from scratch, but can now plug into American or allied networks, leveraging advanced capabilities without the prohibitive cost of full-scale indigenous development. We're even seeing the emergence of entirely new business models for military aviation, like air power as a service. Imagine subscription models where leasing access to sophisticated sensor shooter chains, a network of drones, sensors, and weapons, cost significantly less than the immense burden of maintaining a single squadron of aging F-16s, complete with their own maintenance, logistics, and personnel overhead. This allows nations to acquire cutting-edge capabilities with greater flexibility and lower long-term financial commitment, further reshaping the global balance of power and alliances. Wildcards, space, quantum, and 3D printed squadrons beyond the immediate horizon of AI, hypersonics, and stealth. Several wildcards are poised to fundamentally reshape military aviation in ways that are still difficult to fully grasp. First, space logistics. SpaceX's Starship, a colossal rocket, is designed to lift an unprecedented 100 tons to low Earth orbit for a fraction of the cost of a single B-2 bomber. Imagine the implications. An entire air wing, disassembled and folded neatly inside a rocket, launched on demand to any continent on Earth. It re-enters the atmosphere hours later, rapidly deploys, and then, after the crisis is averted, flies home on its own. Hypersonics already shrink the world by compressing travel times. Space logistics, leveraging the sheer speed and reach of orbital mechanics, threatens to erase oceans entirely as strategic barriers. The Air Force Research Laboratory is actively exploring concepts like Rapid Dragon, which envisions turning conventional cargo aircraft, and eventually potentially even rockets, into airborne aircraft carriers, capable of launching a multitude of weapons or drones from high altitude. This isn't just about faster deployment. It's about global reach and rapid intervention on an entirely new scale. Second, quantum sensors. Today's stealth aircraft rely on deflecting or absorbing radar waves, but quantum sensors could render current stealth technologies irrelevant. A quantum radar, for instance, uses entangled photons to detect even the most meticulously cloaked metamaterial stealth aircraft. The technology is still largely lab-bound, a theoretical marvel, but China has already claimed a 100-kilometer range prototype. If this matures, if quantum radar becomes a viable battlefield technology, then stealth will simply become another layer in a continuous, escalating arms race, rather than a trump card that guarantees invisibility. It forces a whole new generation of counter-stealth technologies and materials. Finally, 3D printing, or additive manufacturing, is rapidly changing the economics and logistics of air power. Instead of waiting months or years for parts, 3D printers are already cranking out drone fuselages in advanced aluminum alloys overnight. The U.S. Marine Corps recently showcased this capability by flying a 30-kilogram Scout drone that was printed entirely from scratch in just 36 hours. The cost, a mere $4,600, break a wing in combat? No problem. Print another one while you sleep. This revolutionizes battlefield logistics, transforming the sprawling, vulnerable supply chain into something as compact and resilient as a spool of wire and a laptop. It enables rapid prototyping, on-demand manufacturing, and unparalleled adaptability in forward operating environments. So, here's the undeniable takeaway, the core truth of where we stand. Air power is no longer just a metal box with a human inside. It has evolved into a complex language spoken by algorithms, a relentless race run at Mach 5 and beyond, a global chessboard that now stretches all the way to orbit. The iconic fighter ace, once the epitome of aerial prowess, is being steadily replaced or perhaps augmented by a new breed of heroes, the coder who trains neural nets, the engineer who prints entire airframes from raw materials, the sharp-eyed analyst who decides which calculated risk is worth a 30-second. Hypersonic flight. The next major conflict, whenever and wherever it may arise, may well be won not by the side with the most traditional aircraft, but by the side that trusts its machines the most. fears its public's reaction the least, and critically, updates its software fastest. Do you honestly think human pilots will still matter in the same way when AI can outturn, outreact, and outshoot any human being in a simulated or real combat scenario? Will the sheer overwhelming numbers of drone swarms make traditional stealth obsolete? Or will stealth simply move into the digital realm, becoming a battle of code and countercode? Drop your view in the comments below. The best argument gets pinned. If you learned something new, something that made you think, please hit like and subscribe. The future is taking off now, and trust me, you absolutely do not want to miss this ride.